Okay. You ready? Okay, next speaker is Ilija Buric. He will talk about Gaudin integrability and then harmonic analysis of conformal partial waves.
Okay, do you hear me? Yes. Okay. First of all, thanks for having me. I wish to thank the organizers and for putting the conference together, which has been most inspiring. I will talk about some work with various subsets of these collaborators, which are Misha Isachenkov, Sylvain Lacroix, Jeremy Mann, Lorenzo Quintavalle, Volker Schomerus, and Zhenya Sobko over the last few years. The general topic is conformal partial waves in higher dimensional CFTs and their relation to integrable Schrödinger problems. Just to say a few words, conformal partial wave decompositions in general in quantum field theory are one of principal analytic are one of principal analytic tools when you want to isolate now? Is it better? Okay. When you want to isolate kinematically fixed part of some amplitude from the dynamics. And for example, in 2x2 scattering, you will have decomposition where all states of spin J will give you a Gegenbauer polynomial of the scattering angle, and then you will have a dynamical function of the energy. In conformal field theory, this idea is completely analogous. So we will have a 4-point function, which is decomposed in kinematically fixed partial waves, which are multiplied by dynamical OP coefficients. And the difference is that now partial wave sums over states that transform in a single representation of the conformal group that propagate. And why we are doing this is the conformal bootstrap. So we should have this in back of our mind. And this is a set of methods for extracting OP data from the crossing equation. So this is the crossing equation. And if you know the partial waves on both sides, in the S channel and in the T channel, then you can cook up some smart functionals and act on this equation. And these people have done this with impressive results. So for example, this is this famous picture for the scaling dimensions of the Ising model, where from a single correlator, you get this bound on the allowed region in the scaling dimension space. And if you consider mixed correlators, then you get a very small island, so which essentially pinpoints down this theory. So in order to study crossing equations, we need these partial waves, and it's very easy to define conformal partial waves as to give an integral representation for them, which is, however, not very useful, and it's difficult to evaluate. And big step in understanding of these functions was made by Dolan and Osborne, who understood that one can write a second-order differential equation called the Casimir equation. They also solved this equation in terms of hypergeometric functions for in even dimensions. But even having the equation is pretty good from the bootstrap perspective, because you can develop fast methods for example, series expansions. in, for example, these radial coordinates. And since the work of Dolan and Osborne, indeed many efficient methods have been developed for computation of partial waves with external scalar or spinning fields. And these include these methods here that I wrote, so differential shifting operators which shift external dimensions, then these expansions in radial coordinates, recursion relations, and then also the weight shifting operators which allow you to construct all partial waves just from scalar ones. And okay, there is also this method which I singled out because it will be important for the talk by Volker, Misha, and Zhenya, who realized that the Dolan-Osborne equations are equivalent to the two-particle integrable Schrödinger problem, which is this BC2 Calogero-Sutherland Hamiltonian. So one of the problems that I will talk about is how about higher point partial waves. Much less is known about them except in low dimensions. In 1 and 2 dimensions, they're known. And if you have only scalar exchanged fields, they are also known. And there is also some work on constructing partial waves for spinning fields, but much less than for 4 points, for sure. And you may ask, why do we want these? And let's say there are two maybe principal reasons to study higher point partial waves. One is, ideally would be to have abstract bootstrap for higher point functions, which we don't at the moment. Although when the points are in light cone configurations, so if you have, for example, 5 or 6 points, so that each two consequent distances are null, then people have already done the Porto group bootstrap, analytic bootstrap in these configurations. But you can also be less ambitious and just compute some higher point correlator in some theory to, for example, to first order in epsilon in the Wilson-Fisher fixed point, and then if you know how to spectrally decompose, then this contains infinite amount of E data. So this would be another useful application if you had higher point partial waves. Okay, so the...
Can you just define this? It feels like that's the theory data.
Sorry?
Higher point waves, what they are. Because what point is always independent of the theory. Higher point where you compare dimensions.
It's independent of the theory. I will come to that in the talk. So yes, the questions that I want to answer or partially answer in the talk are, in what sense are these partial waves integrable, and also to ask, are there elements that you may reasonably call universality in kinds of equations that partial waves satisfy. And some of our results are the following, that in general, for an n-point correlation function, the partial waves can be constructed as eigenfunctions of a particular Gaudin model, which is adopted to this correlation function in the OP channel. And then there are two other results. One is about 4-point functions, and they're related to Calogero-Sutherland models, which is an older story, but maybe the word spinning here is relatively new. And then the 3-point functions of spinning operators turn out to be related to a certain elliptic Calogero-Moser model, which was defined by Tingoff and collaborators. And as a byproduct of this analysis, we will get some relations between these integrable models involved, because on the left, we know that in the conformal field theory, there is a operator product expansion, which allows you to reduce an n-point function to an n-1 point function. And this process produces some relations between these models on the right-hand Okay, so this will be the results, the set of differential equations that completely characterize these higher point waves. And okay, these equations will be hard, but as a first step, we can already see some structural properties of solutions, like factorizations in certain limits. Yes, and okay, this relation between models that I mentioned. Okay, so I will start with the 4-point functions, which is the best studied case, and we know most about it. But I will try to explain how does a relation to these Calogero-Sutherland models come about. So the starting point of this analysis is the two-particle little group, which you can easily see the stabilizer of 2 points inside conformal group, which you can see is isomorphic to this group K. And you can see this if you put 1 point at 0 and 1 at infinity, then you have dilations and rotations which fix this configuration. And then if I look at a 4-point function and view it as a 2-point function of 2 particle states, the space of solutions to word identities is something like this. So I have 2i's G over K, and then word identities tell me that I need to space at the that I need to look at the space of G invariants inside here. And then you can sort of cancel, this is very schematic, one of the G's inside with the G outside, and you get this double quotient by K of G. But notice that K is not any old subgroup, it's what is called a spherical subgroup. So it's fixed by a second order automorphism, and the quotient G by K is a symmetric space. And these types of double quotients were studied since the early days of representation theory by Harishchandra, Gelfand, Gaudin, and other people. And the main player here is this space of KK covariant functions. So you can consider invariant functions, which are invariant under left and right rotation, multiplications by elements of K. But slightly more generally, you can take 2 finite dimensional representations, rho and sigma, and consider vector valued functions valued in this space Hom W right, W left. So W right and left are carrier spaces of rho and sigma. And then this spherical condition is the condition that this space, when you put representations to be trivial, is an abelian algebra under convolutions. So when you have such a pair of G and the spherical subgroup K, then you have a so-called restricted root space decomposition, which is similar to the ordinary root space decomposition. With some slight differences. So we start from the maximal abelian subspace of P, which sort of plays the role of the Cartan. And then we have the centralizer of A in K, which is M, and then some root spaces. And these root spaces are called restricted root spaces. They are with respect to A rather than the Cartan. And then some standard theory shows that we have a spherical decomposition in the universal enveloping algebra, where I can separate, write this as a product as elements in P in A. A is here is abelian, and then 2 copies of K. And on the level of the group, this is known as the Cartan decomposition, KAK, which for SU2 is the decomposition into Euler angles. So the idea, because now we have these spherical functions, if I have a spherical function, if I define it on A, I can uniquely extend it by covariance to the whole of G. So they are effectively functions of only on A. So they depend on dimension A variables. And this dimension is called the real rank of the pair. But really, the main property of these pairs is that you can reduce any differential operator on G, any element of the universal enveloping algebra regarded as a differential operator. If you just decompose this in the universal enveloping algebra, you can reduce this operator to an operator in just the number of variables on AP. So this is the content of Harish-Chandra's theorem, that this decomposition in the universal enveloping algebra allows you to compute the reduction of differential operators in general. And let me give an example. So if you start from this pair, which is of rank 2, that is relevant for me, the conformal group and this group K, when we reduce the Laplacian and then conjugate some first order terms out, which is sort of a trivial step, you get the so-called Calogero-Sutherland Hamiltonian. And this Hamiltonian is related to the root system, and this is precisely this reduced root system of the pair GK. And yeah, so it's exactly. You conjugate out this cot alpha times t, so this will be some first order term. You conjugate it out, and then you will get precisely this Hamiltonian. Yeah, they are very closely related. And then this spin part are these terms. Yeah, so this Hij, Hi, Aj, so these guys are generators of this abelian group A, and they're replaced by partial derivatives, so they become this dt1 squared, dt2 squared. Then you have a term here which also has some elements in H, which become d by dti, and you conjugate those out. And then you have something which is a spin part, which I didn't. When you conjugate this, you will get this one. So when you conjugate out this term, you will get some potential term, and you will get this one, and these constant terms, this one and this one. And then the spin part is this. And I will now say what these terms are. These M1A, M1A, D squared, and so on. So these guys are generators of K. And the point about this formula is that I don't have to tell you what the representations are. So I can tell you only at the end, rho and sigma were particular representations, and replace now in this. Okay, so here I have written the formula when one of the representations is trivial. So I have put rho to be trivial, and sigma will be non-trivial. When both representations are non-trivial, the formula is a little bit longer, and this is why I didn't write it. But if I now want to compute the Hamiltonian with some representation sigma, I will take this formula and replace these generators, which are generators of K, by sigma of them. So this will be a matrix valued, if you will, Hamiltonian. Okay? Does this answer your question? Or? Okay. I will have some more formulas later, so maybe it's... yes, so, and you can reduce any Casimir element, and this is how, one way to see the integrability of the Calogero-Sutherland model is that higher Casimirs give you first integrals. Exactly, so this shows you integrability of the scalar model. So for the scalar model, you will put all these guys to 0, these m's and these. And then you will have the fourth order Casimir, which commutes with this one. And you can check that this eigenvalue problem for this operator is equivalent to these Dolan-Osborne equations that I was mentioning before. Okay, just to say, this is not only abstract nonsense. We used sort of this technology, extended it to supergroups in some earlier work, and the extension to supergroups works like you need to put some nilpotent potential perturbation to this Hamiltonian, and then you can systematically, if you know the eigenfunctions of this guy, you can systematically solve for the eigenfunctions of the supergroup guy. And with this technology, we computed some superconformal blocks in 4 dimensions with Fokker and Zhenya. And another interesting class of systems that fall under this category is defect conformal field theories. And whenever you have a defect, it is also fixed by a automorphism of degree 2. So it's also of this type. And you can see, for example, then that a 2-point function in the presence of a defect, if the defect has codimension 2, for example, this will be exactly the same Hamiltonian up to analytic continuation. So, of course, this is important when you solve for eigenfunctions, the analytic continuation, but at least, yeah. And one more comment, maybe, that these partial waves in ordinary QFT are eigenfunctions of a similar Hamiltonian, just for rank 1 instead of 2. And the solution theory in general for scalar Hamiltonians of this type was developed by Heckman and Opdam, and the eigenfunctions for any root system are these Heckman-Opdam hypergeometric functions. Okay, so now I would like to go to higher points. I think this sort of explains where this solvability comes from for 4 points. But for higher points, the story is very different somehow. Now I come to this point, defining the conformal blocks. So you can see that Casimir operators, so in the 4-point case, Casimir operators measure quantum numbers of the field that propagates. And when you have a higher point function, these kind of quantum numbers are not, there are fewer quantum numbers of this type than cross ratios. And you can easily understand this because if you have a 3-point function, for example, of 2 symmetric traceless tensors and a scalar, this has a the number of tensor structures is greater than 1. So you need some further quantum numbers to specify which tensor structure. If I say, for example, that here is a particular field of spin L1 and here of spin L2, I still need to say what tensor structure at this 3-point function I'm picking. And when you specify all the quantum numbers of the fields and all of these tensor structures at the vertices, then the partial wave is uniquely fixed. You can write this integral representation as a product over the product of 3-point functions. What we did in these works was to characterize also the same partial wave as a solution of certain differential equations which come from the Gaudin model. And in this case, we would have 5 cross ratios and 4 quantum numbers, and the 5th quantum number related to the vertex is measured by this operator, which is a 4th order operator, and the notation here is X is one of the generators of the conformal Lie algebra. So alpha are the indices. So here I am taking the 4th order invariant tensor, and I'm taking the generators at points 1, plus 2, minus 3. So to each point, at each point I have this field representation by differential operators in coordinates of this point. So this is how I construct this operator, and you can easily check that this operator commutes with the Casimir operators. And okay, so how does this generalize to higher points? Okay, so first of all, the space where correlation functions live is the following. So for every point, I have a field representation or non-unitary principal series representation of the conformal group. I take the tensor product of them, and then I need to impose word identities, which means taking G invariants in this space. So this is the space of tensor product of correlation functions. And this is what inspired this, why the Gaudin model is the appropriate one for the following reason. So the Gaudin model is defined when you have n commuting copies of a Lie algebra. You attach them to points z1 up to zn in the complex plane. So these are just parameters of the model. And there is the Lux matrix, which depends on the spectral parameter z, which is constructed as this, sum of generators over z minus zi. And from this Lux matrix, you construct the Hamiltonians by contracting the Lux matrix with invariant tensors, and then adding some correction terms, which are of lower order. So for second order, there are no corrections, but for higher order Hamiltonians, there are these correction terms. And then, okay, these Hamiltonians, of course, commute, but they also commute with the so-called diagonal generators. So if I take the sum over all sides from 1 to n, each of these Hamiltonians commutes with this diagonal action. So this means if I attach to these points not the abstract universal enveloping algebra, but the representation, and I will attach these principal series representations, then these operators become differential operators in all space-time coordinates. But the fact that they commute with this diagonal action means that they reduce to this space of invariance. And this means that I can reduce these differential operators to differential operators that act only in cross ratios. Okay. Right, so what about the parameters? In CFT, actually, we don't have any of these parameters. So we do have parameters, for example, characterizing spins and weights of the fields, but those are of different type, because I already put those parameters in definition of this representation. So I don't have any meaning for these extra n parameters. And in fact, the Gaudin model that will produce these operators relevant for CFT sends all of these parameters either to infinity. One of them is sent to infinity, and then the others are sent either to 0 or to 1 in some particular at different speeds, depending on the OP channel, so the topology of the OP. Yes, so in little more detail, if I take an edge, so maybe just to have in mind, an OP diagram looks maybe something like this or something like this. So if I take any edge, it breaks the set of external points into two disjoint subsets, and I can take the sum over generators of one of these subsets and form this kind of operator, so contract it with an invariant tensor, and these are precisely the Casimir type operators of Dolan and Osborne. And then I can supplement these operators with these vertex operators where I pick a vertex, and then this breaks the set of external points into three disjoint subsets. And then I again contract, but I have one more parameter in the game, so I can pick, let's say, P, or no, here I called it new. So, okay, I pick new generators from one branch and pick P minus new generators from a second branch. And you never need to use all three branches, because word identities tell me that if I take generators or if I sum over all generators and hit the correlation function, I get 0. So the third branch is the linear combination, it's minus the sum of first two branches. Also here in the first definition, I need only to take generators from one of the branches. And okay, in any case, when you do this, you can show, and I have some slides in the back if someone wants to see more formulas, that the Gaudin Hamiltonians in this limit, when you collide punctures at 0, 1, and at infinity, give you precisely these kinds of operators, so these blue and light blue operators. We didn't prove, but we checked up to 10 points that always the number of independent operators that you are left with equals the number of cross ratios. So, yes. And okay, just to show an example how this works. So for example, if you have a diagram like this, this is a CFT correlation function, and I am fusing here two external operators, performing the OP, and then with the result, I fuse it with the third one, and so on. And in the Gaudin model, I will take the sites to be x to some power. So this I is one of these. So depending on the number, I will have a different power, and then I will take x to 0. So this will be the limit. And I will rescale the Lux matrix so that I get a finite quantity. And when you do this, then for every vertex, for example, you get an operator like this. And from these guys, you precisely construct these blue and light blue Casimir operators and vertex operators that I wrote. And if you have a more complicated topology, then if I pick a point, it depends, the way it scales to 0 or 1 depends on a way I go to this point if I start from the top. So every time you go to the right, you need to add a power of x. And in the last step, you need to add a certain power of x as well. It's not very illuminating how it works, but in this picture, for example, there is only one point which is to the right of the top, so only one point will go to 1. All these points will go to 0 at different rates, and the top point always goes to infinity. And okay, so the picture that one gets is something like this. We have some. So how does the counting work? Because the most non-trivial part here then is to really see whether the number of independent operators that you have is the same as the number of operators that you need. Because, for example, if I construct a Casimir from a single site, because I attached an irreducible representation to this site, this is just a number, so this is not an operator. But you can see that the deeper you go in the diagram, these Casimir operators constructed as I said, they will have dependencies, but the deeper you go, you will have fewer dependencies. So at each step, you get one more independent operator. It's like when you have a 4-point function, you have a second-order Casimir and a fourth-order Casimir, and you don't have anything else. But this is true in any dimension, so I don't know, 10-dimensional conformal group certainly has more than 2 Casimirs, but they become dependent, and sorry? Oh, okay, I thought I did, but here is the formula. So I take, so this R is some edge in the diagram. Oh, yeah, first you pick an OP channel, for example, this one, I don't know, but any OP channel. You pick an internal edge, you call it R. Then I have two sets of external points. So the ones that are left of the edge and the ones that are right of the edge. So these are called IR1 and IR2. Then this X, so it's some generator of the conformal group. This index means that I take the sum of generators at all points in this branch. So I take the sum of external generators left of the edge. These are these IR1s. So I use them, okay? So for example, if I pick here, if I pick this edge here, and I look left of this edge, I will be summing over generators of 1 and 2 at points 1 and 2. So by this notation, I put an index is a set, an index is a set, and that means that the object is a sum of generators over all elements in this set. So in this case, IR1 would be the set 1, 2, and the generator would be X at point 1 plus X at point 2. And with the vertex, it's similar, just I have a partition into 3 disjoint sets. So if I pick this vertex, I'll have 1, 2, 3, 4, and 5, 6. Okay. Yes, so, and indeed, so here, for example, you have two external scalars, and in the tensor product of these field representations, only symmetric traceless tensors can appear. So you need two quantum numbers to measure the field that propagates here. And then if you have a symmetric traceless tensor and the scalar, you can have representations with two rows in the Young tableau. So you have 3 quantum numbers, two spins and 1 scaling dimension. And you increase always the number by 1 until you reach the rank of the group, and then you cannot increase anymore. So here I wrote it, I guess, in 4 dimensions, where the rank is 3. And then you can also count the number of vertex operators, and the easiest way to count is okay, this is cheating, but we checked, okay. So you can count it by counting the number of cross ratios and then subtracting this number of edge operators. And this will tell you, for example, that this vertex comes associated with a single vertex operator as well as this one. Whereas in this picture, you have this middle vertex comes associated with 3 vertex operators. But you can also see this in an independent way, like if you consider a 3-point function with a symmetric traceless tensor at one length, a scalar here, and then a mixed symmetry tensor with 2 rows in the Young tableau. And the most general 3-point function, when you write its functional form, it will, okay, so let me write the functional form. So for example, if you have okay, so this is for 2 STTs and the scalar. 3-point function takes the following form. So you have some prefactor times a polynomial of x. So x you construct out of external points in some way, and this polynomial is of finite degree. But morally speaking, you have a single variable, this x, associated to this vertex. And if you do the counting in the same way for a mixed symmetry tensor and the symmetric traceless tensor and the scalar, you will again have a single variable associated to a vertex of this type. Okay, so the system that we studied, how much time do I have? Okay. So the system that we studied with this technology was a 6-point function in this so-called comp topology of the OP channel. So here I will have 6 scalars. And I will consider, so I have a conformal block. So there is a symmetric traceless tensor propagating here, a symmetric traceless tensor propagating here, and then a mixed symmetry tensor propagating here. I pick basis for the space of tensor structures at my two vertices. And I want to say something about conformal blocks defined in this way. So in order, well, okay, so we use the following set of coordinates, which is important. Somehow the coordinates are also adopted to the choice of the OP channel. So for out of the first 4 points, we constructed we use these Dolan-Osborn coordinates Z and Z bar. So these Z1 and Z1 bar are the Dolan-Osborn cross ratios built out of first 4 points, and Z3 and Z3 bar from the last 4 points, and okay, obviously Z2 and Z2 bar from these middle 4 points. And then to define these, so this has 9 cross ratios in total, so the correlation function. Then we have two cross ratios defined in the following way in conformal frame. It's not very important, but yeah, so if you fix the points 3 on a line, and then 2 points will be in some 2 planes, and if you fix this conformal frame, the cross ratio W for these 5 points is defined as the sine squared of half of the angle between these 2 planes. So we have 2 such cross ratios defined in terms of first 5 points and the last 5 points. And then in a similar way, we define this upsilon variable defined in some conformal frame for all 6 points. And then the limit that we will consider is that all these 3 middle variables go to 0. And physically, this means that points 4, 5, and 6 become close to each other. So the distances between these points become 0. And then writing this, there are 9 differential operators coming from the Gaudin model. And in this limit, 3 cross ratios disappear. They're sent to 0. So there are 6 remaining operators in the limit. But what happens is they all they factorize in 3 left variables and 3 right variables. And then the conformal blocks in this limit factorize as products of these left variables and right variables. And moreover, you can check that the quadratic Hamiltonian, so the quadratic Hamiltonian of the Gaudin model, it's a 3-variable operator. When you compute it, is the same as this spinning Calogero-Sutherland model, and the spinning model for such a 4-point function, where you have 3 scalar fields and then a field which is a mixed symmetry tensor with 2 Young tableaus. And just to show a formula, so this is this operator. So it's a special case of the operator that I showed in one of the first slides, but now I put, for these abstract generators, I put their representatives in this mixed symmetry tensor representation, and they come with this variable x. So this is this spinning Calogero-Sutherland model, and it depends on quantum numbers of this field. Okay, just to say similarly, we looked at the reduction of a similar type on a vertex, where the model that you get in the limit is this elliptic Calogero-Moser system that was found by Tingo, Felderma, and Veselov. And again, the parameters of this elliptic system, they are related to quantum numbers of this field. Okay, so let me conclude. Okay, so for any correlation function and the choice of an OP channel, we have this limit of the Gaudin model such that Hamiltonians compute, well, the eigenfunctions coincide with partial waves. We introduce these coordinates which are compatible with taking OP limits and observe this factorization in this particular limit. In particular, this does show that, for example, you get this spinning Calogero-Sutherland model or this elliptic Calogero-Moser model as reductions of Gaudin in this limit. Some directions for the future. Well, one thing interesting for conformal bootstrap applications would be to look at the light cone limit in a 6-point function, and this is being done at the moment. Yes, so similar to what people have done for the 5 points, where you can get some bounds on OP data by analyzing this limit. Well, conceptually more difficult would be to formulate also the numerical bootstrap for higher points, and this is something we are thinking about, but it's complicated. Then, okay, what about solution theory? This is not really a usual type of Gaudin model because we have these infinite dimensional principal series representations attached to sites. So some of the techniques do work, like if you are in one dimension, then it's possible to go to momentum space. Well, okay, it's possible to do separation of variables, and these separated variables turn out to coincide with momenta, and to construct eigenfunctions in this case. But yeah, it's not easy to do bootstrap, for example, in momentum space. So there's some caveats there. But I think a very promising way to construct eigenfunctions would be to use these weight shifting operators, similarly to what people have done for 4-point functions. Our sort of initial idea was to analyze this whole system by reducing it to different vertices and different 4-point diagrams inside, for both of which we sort of know solutions, and build conformal partial waves by somehow combining these vertex eigenfunctions and 4-point eigenfunctions. But it's in the future. It's not so clear how to do it. Among other directions is this universality. You can actually apply this spinning Calogero-Sutherland models appear also for some higher point functions involving defects, where you can somehow transfer some of the spinning. Well, if you have a higher point function, you can treat some of the space-time degrees of freedom as spinning degrees of freedom and map it to a spinning Calogero-Sutherland model with an infinite dimensional representation. And so this is something we've been looking at with Volker. And also the extension of this Gaudin, with this correspondence to Gaudin models to systems with defects include these cyclotomic Gaudin models. And finally, one can also look at ordinary quantum field theory, and spherical functions are also relevant there for computation of ordinary partial waves, which is, I don't know, I mean, it's an important problem. Then you can start looking at scattering of gravitons and photons, for which these partial waves are important. So it's also something that will be interesting to look at. That's it.
Thank you, Ilija. Thank you for the very interesting seminar. So, are there any questions?
So when you do this conformal cross ratio, Z1, Z2 up to many, and W's.
Sorry, can you?
So when you did decomposition of 6-point function into two, like in the middle, that's that's exactly what you declare you want here. Yeah, so now you kind of have this new partial wave with many points. That's okay. But it feels like you choose conformal cross ratio like very manually, like you design conformal cross ratios Z1, Z1 bar, W1 very manually. There are many other choices presumably you can make.
Yes, yes.
And then you say this choice gives me spinning Calogero-Sutherland.
Yeah.
It's good representation because we can see something, but the further you go, the more cross ratios you will be. There are systematics that you can do.
Yeah, well, already, like, for 4 points we have Calogero-Sutherland. If I go to generic configuration in 6 points, I don't have something like this. And indeed, like Gaudin and the Calogero-Sutherland, I would say, are completely different. So the Gaudin is super general integrable model. So I can adopt it for any for any endpoint function with anything. I mean, I can also put spinning external fields and so on. The Calogero-Sutherland story is very special, and it applies to this 4-point case and to some cases with defects, and it's not going to appear in general cases for sure. But yeah, one of the things that we are exploring is what is the space of cases where you can reduce the problem to a spinning Calogero-Sutherland, and yeah, for sure not all higher point functions.
Okay, and you mentioned duality between integrable models. I think it's in your plan of the talk at the very beginning. You mentioned new relations between integrable models.
Yes.
Which ones? Where it was?
So, for example, yeah, okay, for this system, we have a Gaudin model associated with this system with 9 independent Hamiltonians. And then the statement is that if you take this Gaudin model with this principal series representations and look in the limit where these 3 variables are sent to 0, then the Gaudin Hamiltonian, the quadratic Gaudin Hamiltonian, becomes the spinning Calogero-Sutherland Hamiltonian. And also, in this case, similar.
So it's something completely new, right? People did not know these things before.
No,
okay.
No, they didn't. Yeah.
Okay. Further question?
I have a conceptual question. So does this correspondence to this Calogero model helps in calculating 3-point functions or 4-point functions analytically?
Well, this is purely kinematics, what we are looking at. So, no.
More questions?
I mean, if you do bootstrap, then yes, but like, the way bootstrap functions, you put this into the crossing equation, and then from the crossing equation, you get bounds, either numerical or analytical, on the OP coefficients. But you need to go through this analysis, which is the more difficult part of the analysis.
Yeah, so how does your construction depend on the details of the conformal field theory you're considering?
It doesn't. So it's just kinematics. It works for any conformal field theory.
And let's suppose that we want to look at our favorite conformal field theory, let's say n equals 4 super Young mills. In the planar limit, there is some integrable structure. Does this integrable structure knows anything about the other?
I would say no. I mean, I don't think so. Well, also, like I don't think this has been too much explored. So we looked at super conformal theories computing the blocks actually from our side, supersymmetry adds quite a lot of complications. So to compute superconformal blocks when you have long operators is much more difficult than to compute them in a bosonic theory. And for n equals to 4, no one really, for n equals to 4 supersymmetry, no one really computed these blocks except for all half BPS operators. So I think this what we looked at was n equals to 1 with 2 long and 2 short operators. And I think this is the only crossing equation with all conformal blocks put in 4-dimensional superconformal theories which is not only for short operators. So maybe if one computed these superconformal blocks for n equals to 4 theories, maybe something would be seen, but in general I don't expect. They just get more complicated when you increase supersymmetry.
Okay, thanks. And I have another conceptual question. Does this help for bootstrap? For example, can one use this kind of information for if you want to do bootstrap?
You mean of higher point functions, or?
Yeah, let's say.
Yeah, so it helps. So, for example, sorry, which slide? Yeah, so what Vaško, Raul, and Shinan did in this paper was they computed in n equals to 4 a 5-point function of this O2 operator, and well, in super-Greif limit in expansion, and they spectrally decomposed it. And when you have a 5-point function of this operator, there are many non-protected operators that appear in the OP that propagate there. And by spectrally decomposing a single correlation function, they got a wealth of OP data to this order. So if one, but this is a very hard computation. So it's not just you can sit down and do it, but if people could, then this would give an enormous amount of OP data. So this is the goal, or one of the directions.
So further questions? So if there are no further questions, we can thank again Ilija. We have now a half an hour break.